Welcome to our second video on permutations with distinguishable objects. In this video, our goal will be to continue to develop our understanding of permutations, but we're going to dig a little bit deeper into problems that involve various conditions. Now, as we explore these problems, we're going to use both equations and technology to help us solve them. Before we dig into our examples, let's just remind ourselves of that equation or that formula that I just mentioned. Here's the equation that we use to determine the number of permutations when all objects are distinguishable. Now remember, n is the total number of objects that we can choose from, and r is going to be the number of objects that we're going to select for the permutation, or the number of objects that we're actually ordering. I can't stress enough how important it is or how helpful it is to draw out diagrams before you start calculating. We're going to use this strategy a lot as well. All right, let's dig into this first example. It says, at a used car lot, 7 different car models are parked close to the street for easy viewing. Part A says the 3 red cars out of those 7 must be parked so that there's a red car at each end and a third car is exactly in the middle. I'm guessing the car lot thinks that that will catch people's attention. It wants to know how many different ways can these 7 cars be parked. We'll dig into part B after we finish up part A. Now, like I mentioned previously, it's often really helpful to visualize what's going on in the car lot, in this case, by drawing a diagram. So I'm going to start by drawing out my 3 red cars. I've got 1 on each end and 1 in the middle, and I'm just going to use squares to represent the cars. Doesn't have to be anything fancy. Now, in between those red cars, I've got the other 4 cars. It doesn't say what color they are, so I just colored them as I wished. So when I'm analyzing this problem, let's look at this from the red car perspective and the other cars. Let's label them. Now we've got 3 red cars and it's asking us to order all 3 of them. So if we bring up our permutations equation here, NPR equals n factorial over n minus r factorial, and I can plug in my values for n and r, they're both 3, and you can see here that I end up with essentially 3 factorial. So remember, if I've got 3 objects and I'm ordering all 3 of them, that is just equal to n factorial. So there are 6 ways to order those red cars. Now we also have to order these other 4 cars, and so we've got 4 cars and I need to order all 4 of them. So n will be equal to 4 and r is also equal to 4. Now I can use my permutations equation here. However, I just realized that it's just going to be n factorial. So in this case, 4 factorial is equal to 24. Now, to find the total number of ways to park the 3 red cars and the 4 other cars, we're going to multiply them together. Remember that keyword and tells us we need to use the fundamental counting principle and multiply them together. So here's my total: 6 ways to order the red cars, and there are 24 ways to order the other cars, which means that there are 144 total ways to order the cars. Moving along right to part B. Now, in this scenario, it says that the red cars must be parked side by side. We're going to start this just like we did part A, and we're going to draw a diagram. The problem indicates to us that the red cars must be parked side by side. However, it doesn't stipulate that the cars must be in a specific location within the lineup. So for example, the 3 cars could be at the beginning of the lineup, in the middle of the lineup, at the end, and so on and so forth. Now, since the red cars have to stay together, I'm going to represent these 3 red cars with one large box, and I'm going to consider them as occupying one spot that's available in the lot. We also know that the 3 red cars can be lined up differently amongst themselves. So there would be 6 different ways to order those 3 cars, or there's 3 factorial ways to order those 3 cars. Now, if we're considering that the 3 red cars represent one spot, and we've got these 4 other cars that we need to order, let's call this 5 total spots to be ordered. So we've got these 3 red cars to be ordered, and we have these 5 spots to be ordered as well. So that's the 4 cars that are on their own that are not red, along with this one big spot that all 3 of those red cars would occupy. Ultimately, that means we've got 3 pick 3 and 5 pick 5. And we know that just means that we're going to do 3 factorial multiplied by 5 factorial, which gives us 720 possible lineups that can be created at the front of the parking lot. All right, our last example here is going to be about social insurance numbers. This is another great example of a permutation. Now, in this case, Canada's SIN numbers, or our social insurance numbers, consist of 9-digit numbers, and we can use the digits 0 through 9. Now, we're going to look at 2 different scenarios here, or 2 different conditions. The first is that there are going to be no restrictions on the digits that can be selected for each position in the number. And it wants to compare that to how many possible SIN numbers we could create if no repetition is going to be allowed. So we'll break these down into 2 different scenarios, and then we'll compare them at the end. Let's start with this scenario where there's no restrictions, or that means that repetition is allowed. So in this case, we can choose from all possible digits, 0 through 9, for each digit of the social insurance number. So I'm just going to draw out 9 blanks here that are going to represent each digit in the SIN number. Now, because it's possible for me to use all digits from 0 through 9 for each of these blanks, there's going to be 10 possibilities that can go in each of these blanks. So in order to determine the total number of SIN numbers, we simply need to go 10 times 10 times 10, 9 times, but we can be smarter than that. We can use a power of 10 here. So the number of SIN numbers is going to be 10 to the power of 9. 9 is the number of digits that we are selecting. So ultimately, then we can make 1 billion different SIN numbers. So let's compare that to if there are restrictions allowed, or that means that we cannot repeat any of the digits within that 9-digit SIN number. So in this case, we've got 10 digits to choose from, and we are going to order 9 of them, and they all are going to be distinguishable, which means in this case, we can use our formula for permutations. So n is going to be equal to 10, and we are ordering 9 of them, so r is going to be equal to 9. So here's our equation for NPR, where 10 P9, so we've got 10 factorial, all divided by 10 subtract 9 factorial. Now this leaves us with just 10 factorial divided by 1 factorial, which is really easy peasy. That means we've just got 10 factorial and we can evaluate that. So you can see we've got 3,628,800 possible SIN numbers if repetition is not allowed. So the question asked us to compare the two. So if 1 billion are possible if repetition is allowed, and we've got just over 3.5 million that can be created if repetition is not allowed. So the difference between that would be 996,371,200. So that is a pretty significant difference in the number of SIN numbers that could be created. Now that we've looked at a few problems, let's summarize what we've learned in this video, part 2 of permutations with distinguishable objects. We've continued to apply the permutation equation to solve problems where restrictions are involved this time, and drawing diagrams and representations of the problems are key to helping us analyze the restrictions prior to trying to solve the problem.